Which of the following statements is true about sklearn's Gaussian random projection for dimensionality reduction? A Gaussian random projection generates a random matrix with normally distributed elements. B. It projects data onto a lower dimensional subspace using a random matrix with a specified number of components. C. It is often used when dealing with high-dimensional datasets and can be effective for preserving the data's essential structure. D. All of the above. Correct. Gaussian random projection uses a random matrix with elements drawn from a Gaussian distribution, which is a normal distribution. This random matrix is the key to projecting data onto a lower dimensional space. A Gaussian random projection generates a random matrix with normally distributed elements. Correct. The Gaussian random projection method takes data points and projects them onto a lower dimensional subspace. The components parameter controls the number of dimensions in this subspace. B. It projects data onto a lower dimensional subspace using a random matrix with a specified number of components. Correct. Gaussian random projection is particularly valuable for high-dimensional data, as it can reduce the number of features while trying to preserve essential relationships within the data. C. It is often used when dealing with high-dimensional datasets and can be effective for preserving the data's essential structure. Correct. All the statements A, B, and C accurately describe the key features and applications of Gaussian random projection. D. All of the above. D. All of the above. Techniques to reduce the number of features dimensions in a dataset while trying to preserve the essential information. This can be beneficial for tasks like visualization, speeding up algorithms, and improving efficiency. Visualizing high-dimensional data, which is impossible to plot directly in its original form. Speeding up machine learning algorithms by reducing the computational complexity. Improving efficiency when analyzing large datasets with many features. Imagine a dataset with 100 features dimensions. You can apply a dimensionality reduction technique to reduce the number of features to, say, 10, while still preserving the essential information. This can make analysis and visualization much easier. A bell-shaped probability distribution that is symmetrical around its mean. It's often used to model real-world phenomena like heights, weights, or test scores. Analyzing human heights, which tend to follow a normal Gaussian distribution. Modeling the distribution of errors in measurements, which can often be approximated by a normal distribution. Creating realistic simulations of data by generating random numbers from a normal distribution. In a dataset of student scores, the average score might be 75, and the scores might be distributed around this average following a Gaussian normal distribution. A matrix whose elements are randomly generated according to a specified distribution. This is useful in various areas like dimensionality reduction, cryptography, and statistical analysis. Generating random noise in simulations or data analysis. Constructing random projections for dimensionality reduction techniques. Creating cryptographic keys or other security elements based on randomness. A 3x3 random matrix could have elements generated randomly between 0 and 1, or according to a specific distribution like the normal distribution. A lower dimensional space that is a subset of the original higher dimensional space. It can be thought of as a plane or line within a 3D space, for instance. Visualizing high-dimensional data by projecting it onto a lower-dimensional subspace, example a 2D plane. Solving linear systems of equations, where the solutions lie within a subspace of the original vector space. Understanding the relationships between variables in a dataset by examining their projections onto subspaces. Imagine a 3D space. A plane within this space is a 2D subspace. A line within the space is a 1D subspace. Parameter in Gaussian random projection that specifies the desired number of dimensions in the projected space. It determines how much dimensionality reduction is performed. Choosing the number of dimensions to reduce data to for better visualization or computational efficiency. Experimenting with different levels of dimensionality reduction to find the optimal balance between data compression and information preservation. Adjusting the components parameter to control the complexity of a machine learning model. If a dataset has 100 features, you might set components to 10 to reduce the dimensionality to 10 features, or you might experiment with other values to find the best reduction for your task. The process of creating new features from existing ones to improve the performance of a machine learning model. This can involve transforming data, combining features, or creating entirely new ones. Combining multiple features to create a more informative feature, example creating a feature total amount from quantity and price. Transforming features to make them more suitable for a model, example taking the logarithm of a feature with a skewed distribution. Creating new features from existing ones to capture specific patterns or relationships in the data. Instead of using separate features like height and weight, you could create a new feature body mass index by dividing weight by height squared. This new feature might improve a model's performance. You have a high-dimensional dataset with sparse features. Which of the following considerations are important when choosing sparse random projection for dimensionality reduction? A. Sparsity of the transformed data. Sparse random projection preserves sparsity in the transformed data. B. Computational efficiency. Sparse random projection is computationally efficient, especially for high-dimensional sparse data. C. Data distribution. Sparse random projection assumes a uniform distribution of data points in the high-dimensional space. D. All of the above. Correct. Sparse random projection is designed to handle sparse data effectively, and it preserves the sparsity structure in the transformed data. This is crucial for datasets with a large number of zero-valued features, as it avoids introducing unnecessary density, which can be computationally expensive and lead to information loss. Sparse random projection is particularly effective for datasets with sparse features because it preserves sparsity while reducing dimensionality. Correct. Sparse random projection's computational efficiency is a significant advantage. The algorithm leverages the sparsity of the data to perform operations quickly, making it suitable for high-dimensional datasets where traditional methods might struggle due to computational complexity. It leverages random projections to create a lower dimensional representation, which is computationally efficient, especially for high-dimensional sparse data. Correct. Sparse random projection relies on the assumption that the data points are uniformly distributed in the high-dimensional space. This assumption is common in dimensionality reduction techniques, and while it may not always hold perfectly, it allows sparse random projection to work well in many scenarios. It assumes a uniform distribution of data points, a common assumption in dimensionality reduction methods. Correct. All the provided statements are correct. Sparse random projection excels in preserving sparsity, computational efficiency, and relies on the assumption of uniform data distribution. Sparse random projection is particularly effective for datasets with sparse features because it preserves sparsity while reducing dimensionality. It leverages random projections to create a lower dimensional representation, which is computationally efficient, especially for high-dimensional sparse data. It assumes a uniform distribution of data points, a common assumption in dimensionality reduction methods. All of the above. The process of transforming high-dimensional data into a lower-dimensional space while preserving important information. It's often used to reduce computational cost, improve model performance, and make data visualization easier. Image recognition, reducing the dimensionality of image features for faster and more efficient classification. Text classification, representing documents as lower dimensional vectors for sentiment analysis or topic modeling. Recommender systems, identifying patterns in user preferences from high-dimensional data for personalized recommendations. Data where most values are 0. This is common in text data, images, and other applications where information is often sparse and non-continuous. Text analysis, representing words or phrases as sparse vectors with non-zero entries indicating their occurrence in a document. Image processing, representing pixels in images as sparse vectors for image compression or noise removal. Projecting high-dimensional data onto a lower-dimensional space using random matrices. This technique is efficient for dimensionality reduction and often preserves the essential information in the data. Data exploration, visualizing high-dimensional data in a lower-dimensional space for pattern discovery. Machine learning, reducing the dimensionality of features for improving the performance of classification and regression models. The speed and memory usage of a process or algorithm. It is crucial for handling large datasets and achieving real-time processing. Image processing, optimizing algorithms for real-time object detection and tracking in video streams. Natural language processing, processing large volumes of text data efficiently for sentiment analysis or machine translation. Data points are spread evenly across the space. This assumption is often made in dimensionality reduction techniques to ensure that all dimensions are treated equally. Clustering, assuming that data points in each cluster are uniformly distributed to group similar data points together. Anomaly detection, identifying outliers in data that deviate significantly from the uniform distribution. Real-world applications where dimensionality reduction with sparse random projection can be beneficial. Text classification, reducing the dimensionality of text features for spam detection or sentiment analysis. Image recognition, reducing the dimensionality of image features for faster and more efficient object detection. Recommender systems, identifying patterns in user preferences from high-dimensional data for personalized recommendations. You have a dataset with 10,000 features. You want to reduce its dimensionality while preserving the distances between data points. You decide to use the Johnson-Linden-Strauss JL lemma and the random projection. Johnson-Linden-Strauss MindIm function in sklearn. What is the minimum number of dimensions needed to achieve a 95% accuracy in preserving distances using the JL lemma? A 100, B 1000, C 10,000, D 100,000. Solution: false. 100 dimensions are likely too low for preserving distances with 95% accuracy in a dataset with 10,000 features. The JL lemma suggests a higher dimensionality is needed for this level of accuracy and the number of data points. Solution: true. 1000 dimensions is a more realistic estimate for preserving distances with 95% accuracy given the number of features and the desired accuracy. This is based on the JL lemma and the output of the John-Sonlin-Den-Strauss-Mindem function. Solution: false. 10,000 dimensions is the original number of features and does not represent dimensionality reduction. The JL lemma aims to reduce dimensionality while maintaining distance relationships. Solution: false. 100,000 dimensions are too high. The goal of dimensionality reduction is to reduce the number of features, not increase it. The JL lemma aims to find a lower dimensional representation that preserves distances. B1000. Related concepts. Curse of dimensionality. As the number of features increases, data becomes sparse and distances between points become less meaningful. Imagine a spam detection model. With a high number of features representing email content, it becomes challenging to effectively classify emails as spam or not due to the sparsity of data in high dimensions. Related concepts. Principal component analysis (PCA). A linear dimensionality reduction technique that finds the principal components' directions of highest variance in the data. In a customer segmentation model, PCA can be used to reduce the number of customer features, example age, income, purchase history, to a smaller set of principal components that capture most of the variance in customer behavior, aiding in identifying customer segments. Related concepts. T-distributed stochastic neighbor embedding (TSNE). A nonlinear dimensionality reduction technique particularly useful for visualizing high-dimensional data. Visualizing gene expression data with hundreds of genes can be challenging. TSNE can help reduce the dimensionality to a 2D or 3D representation, allowing us to visualize patterns and relationships between genes. Related concepts. Manifold learning. Explores the idea that high-dimensional data might lie on a lower-dimensional manifold, enabling the discovery of underlying structures. In image recognition, manifold learning can be used to find underlying structures in high-dimensional image features, helping to better understand the relationships between images and improve image classification accuracy. Related concepts. Feature selection. Selects a subset of relevant features from the original set, often based on criteria like information gain or correlation. In a credit risk assessment model, feature selection can be used to identify the most important factors influencing creditworthiness, example income, debt-to-income ratio, credit history, simplifying the model and improving its accuracy. Use cases. Computer vision. Reducing the dimensionality of image features for faster image classification and object detection. A system that classifies images of animals can use dimensionality reduction techniques to reduce the number of features extracted from each image, making the classification process more efficient without compromising accuracy. Use cases. Natural language processing (NLP). Reducing the dimensionality of text representations, example word embeddings for tasks like sentiment analysis and topic modeling. A sentiment analysis model can use dimensionality reduction to reduce the number of dimensions in word embeddings, leading to faster analysis and more accurate sentiment prediction. Use cases. Bioinformatics. Analyzing gene expression data with thousands of genes, reducing dimensionality to identify patterns and relationships. A study analyzing gene expression data from cancer patients can use dimensionality reduction techniques to identify the genes that are most significantly associated with the disease, leading to a better understanding of the underlying biological mechanisms. Use cases. Recommender systems. Reducing the dimensionality of user-item interactions to recommend relevant products or content. A movie recommendation system can use dimensionality reduction to represent user preferences and movie characteristics in a lower dimensional space, leading to more effective and personalized movie recommendations.